All right, let's get started. Thanks everyone for coming to my talk. My name is Tiark Rompf. I'm an assistant professor at Purdue University, and if you don't quite know where that is, then we're a little bit south of Chicago in the United States. And before I came to Purdue, I was actually in Switzerland, in Lausanne, for a number of years, and I was a member of the team that developed the Scala programming language. And of course, you know that, well, Spark is implemented in Scala, and there are many connections between the two systems and communities. And actually, the first time I learned about Spark was back in the day at Scala Days 2011, when a guy named Matej Zaharia gave a talk about this cool new cluster computing framework that had these amazing speedups over Hadoop, which back then was the state of the art, right? And how did Spark do that? Well, instead of going all the time to disk to fetch data, you had an option of keeping data around in memory, right? So that was very good, and that led to speedups of like 40x or 50x, right? Crazy numbers. And I'm really impressed by how things have progressed since then, right? So in those 5 years, Spark has made amazing progress, and it started out as a library that was getting lots of good speedups by just keeping data in memory using a very simple trick and using these abstractions of RDD, which allow you to trace the lineage of computations, and getting fault tolerance without storing stuff to disk all the time. Right? But since then, Spark has improved a lot, so it's no longer just a library. These days, there's a full relational query optimizer, which is called Catalyst. And there's even a code generation component which generates JVM code that is then becomes part of the underlying RDD execution engine. Okay? So lots of work in terms of performance optimizations, lots of new architecture, lots of state-of-the-art techniques. So the question I've been thinking about and sort of what motivated the work I'm going to show you is, well, how fast is Spark really in practice? And I'm an academic, I work at a university, I like doing research, so let's use the scientific method and do some experiments. And I've downloaded a data file from the Google Books project, so this is a file where the occurrences and the relative, how many times a certain word occurs in all of Google Books is recorded. And you can download bits and pieces of this data set. So I've just downloaded a file which contains all the occurrences of words that start with the letter A. And so this is in total a 2 gigabyte file, so not something you would really call big data, but it's still sizable to process this on a laptop. Okay? And we're going to use Spark to do some computations with that. Right? So it's pretty easy to do. We just have to define a schema for this file, and then we just define this as an intermediate table, and then we can use actual Spark SQL statements to do some processing with that. And note that I'm running Spark in single core mode here, because I'm not so much interested right now in the scalability aspect, but really in, okay, what are the overheads on a single core on a single machine? Okay, so let's load the data schema. I have this in a file called demo.scala. Okay, there we go. And now we can do something like define a new data set. So this is spark.sql. And then we can, for example, say select star from gbooks where word is some random keyword. So I grew up in Germany, moved to the US, so I think this might be appropriate. And so this will not run any query yet, it will just give us a data frame, but now we can go ahead and call show on it. And we're interested in how long this will take. So let's just do this. Whoops, so that was very fast, right? And well, the reason it's fast is because the keyword just occurs at the top of the file and it will only print out 20 rows. So let's do something more interesting. Let's actually say we're looking for 1,000 rows and make it traverse the whole file. And well, you can see that this is not quite so fast, right? So we get some status bar indicator. There are several stages here. So this already looks like it's going to take some time. So while we're waiting for the result, we can actually think about, well, maybe Spark is a little bit overkill for such a simple task, right? It's nice that we're able to write the SQL statement, but we don't really have to, okay? So we could do something simpler. We could go ahead, for example, and write a little piece of Scala code that does the processing for us, just manually, right? So there's no SQL engine here, no relational query optimizer, just a handwritten program that does exactly the same thing, okay? So the Spark program is still running, right? So, there we go, right? So we get a result back, and I've been printing the time it takes, so this was 55 seconds, right? So about a minute to traverse a 2 GB file. So let's take a look at how long the handwritten Scala program takes. So we can launch that, and we already get some results because, well, these are at the top of the file. And we can wait until this is done and compare how long this would take. Okay, so this was much faster, right? That's 13 seconds, right? So you can see by writing the code by hand instead of using a cluster framework like Spark and a relational query optimizer, we can get much better in terms of performance. So what I'm going to show you now is, and this is part of the research that we've been working on, we've built an accelerator module for Spark that is able to get to even better performance than the code we've been writing by hand. Right? And the way I can use this, so the system is called Flare, I can use it on any Spark data frame, and when I use Flare of Q here, then I get back an object of type flaredf, right? So that's a Flare data frame, and when I now call show on this Flare data frame, then, well, we can say how long that takes. Right, so first there's a compilation step. I will talk about that in a little while. That takes 52 milliseconds, and whoops, then we get our result blazing fast in only 5 seconds. Right, so that's more than twice as fast as the handwritten Scala code. So how does that happen? Well, one key reason is that we're actually doing native compilation here. So we're not generating code that runs on the JVM, but we're generating machine code that runs outside in a separate process and does the data processing. Right? And it's not really intuitively clear why this would get you a lot better performance, because usually you would have the assumption that, well, the JVM is pretty fast these days and it will do a lot of things to optimize your code. But in practice, it's actually, even though the JVM is an amazing piece of technology and does lots of just-in-time compilation and runtime profiling and so on, getting really top performance out of the JVM is actually a very hard problem. Right? So you have to use exactly the right code to trigger the optimizations that you really want. Okay, so this is what Flare can do, and well, you can say, well, that's not a super interesting use case here. So we're interested in actual SQL workloads. Okay, so let's do some actual SQL processing, and so I have the TPCH benchmark here. So that's an industry standard analytic benchmarks. It has 22 queries, and let's just take a look at one of them, which is quite simple. So this is query 1 from the TPCH benchmark, right? So it's basically just traversing one table, which is called line item, and there's a filter, and then there's a few aggregates. So if we are computing some aggregates and have a group by statement here, okay, and then there's a sort at the end. So let's see how that fares with Spark. So let's create our data frame, and this is again spark.sql, and now we're just using TPCH Q1 here. Okay, and let's see how fast that runs. Okay, so again we see a progress indicator, so clearly it's doing some work under the hood, and again we can wait for the result and wait some more and some more, and okay, so this was faster, so it's not quite a minute, but it's still 16 seconds. Okay. So let's run the same thing with Flare. So all I need to do is I need to say, well, I want to run Flare of Q and do show. And there we go, 2.5 seconds. Right, so again, you can see, well, there's almost almost an order of magnitude difference here. And now we can sort of start doing more interesting things, right? So here we're still reading CSV files, so we can say, well, what happens if I convert my data to Parquet format, right, which is an efficient columnar representation, or I can preload my data, so Spark has facilities for all of this. But essentially, we can see the same pattern and show the same kind of speedups here. So let's just go back to slides and talk about how all this works. So I showed you this diagram with the current Spark SQL architecture, and sort of what we identified as bottlenecks is actually kind of a legacy from the old days of Spark, when Spark was just a library and did not have any compilation step. And that is essentially the RDD level, right? So RDDs are really great for fault tolerance, but fault tolerance really only matters when you're running stuff on a cluster of 100 or 1,000 nodes, right? So if you're really working at Google scale or Facebook scale, then you absolutely want to have fault tolerance because components are failing all the time. But if you're working with some realistic workloads, so you're not Google or Facebook, but you still have some data in the range of a few tens or a few hundred gigabytes, then you can run that on a cluster of a few machines, or even on a large server class machine, which is just one box but has multiple CPU sockets and large memory, right? So you can go to Dell and buy machines with a terabyte of memory, and you can even rent them from Amazon, right? So that's a pretty affordable thing. And in such a scenario, you don't really need fault tolerance, right? So the whole RDD abstraction kind of gets in the way. So what we're doing in Flare is we're replacing the bottom layer. We're taking the optimized query plans that come out of the Catalyst optimizer, and we're going into our own compiler pipeline here. Right? So this is based on a previous project that was done at Stanford and EPFL. The system is called Delight, and it's a compiler framework, so you could think about it like LLVM, but it's a bit higher level, so it's geared towards domain-specific languages. And essentially what we're doing with Flare is we're just saying that SQL or Catalyst query plans are another domain-specific language, right? So we're mapping the Catalyst query plans to our Delight intermediate language, so this is called DMLL, or Distributed Multi-Loop Language. And from there, we have multiple optimization passes, we can do efficient parallelization, and so on. And at the end, we can generate code in a variety of languages, right? So right now, we're generating C code, and we could also generate LLVM, so there's not such a big difference. And then there's a small runtime component which orchestrates parallel execution at runtime. Good. So let's look at some more results. So I showed you some very simple things in the demo, but we've actually done a lot more benchmarks on what we consider realistic use cases. So in particular, we looked at all the 22 queries of the TPCH benchmark, and you can see that across the board for all of these queries, you see basically an order of magnitude speed up, right? And if you look at the diagram, so here we're comparing Postgres, Spark SQL, and Spark SQL accelerated with Flare. Then if we just plot the absolute running time in milliseconds, then the Flare bars are so small they don't even show up, right? So we have to go to log scale to actually see anything interesting, right? And here you can notice that any doubling of the bars is an order of magnitude difference here, right? So very, very good speedups on a small data set. So scale factor 1, SF1, that's just 1 gigabyte, so not that interesting in practice. But we can observe the same thing for larger scale factors as well. So here's scale factor 10, still running on a single core, this time not on a laptop, but on a bigger machine, but we're using just a single core. And you can see the same pattern, right? Order of magnitude speedups. So once we know how to run stuff efficiently on a single core, then obviously we want to parallelize, right? We do want to go to multiple cores and potentially multiple CPU sockets. Okay, and we have our intermediate language. We know how to parallelize things. So we get pretty good parallel speedups as well, right? So here we're running on a server class machine. And you can see that, well, just by using OpenMP or pthreads or any standard parallelization tool and being sort of slightly clever about how to arrange things, we can get pretty good scaling up to 16 cores. right? So we don't really see linear speedups here because the sequential bench line is heavily optimized and uses slightly different data structures than the parallel ones, right? So we can't really expect to get linear scaling here, but scaling is still pretty good. But one thing we can observe on these big server class machines is that once we go to higher core numbers, and this machine has 72 cores, once we go to 32 or 64 cores, then we kind of get these bathtub curves, right? So things start to get slower again. And in order to understand what's going on here, we really have to look at the architecture of these machines, right? So all of these machines have more than one CPU socket. In this case, we have 4. And each of the CPU sockets has its own memory attached, right? So our machine here has 1 terabyte of memory in total. And that is split in 4 parts, so 256 gigabytes are attached to each of the CPU sockets. Right? And that means if you're not careful about your memory accesses, then if you want to access memory that's attached to a different CPU socket, then you have to make a request on the bus, and then there are cache coherence protocols and so on. So a whole lot of things have to happen that will really slow down your processing time. But since we're generating code anyways, and we know the architecture of the machine, we can do a lot of tricks. So we can pin our threads to particular cores. We can arrange the data in memory that to make it NUMA-aware, that we can have mostly local memory accesses. And once we do that, we actually see very good scaling up to 64 cores. Right? So again, this is not a doubling for every doubling of core numbers, but we would not really expect this. But we still get faster for up to 64 cores, right? Which I think is a pretty nice result. So what we can observe here is that we're processing this 80 gigabyte file in only 250 milliseconds on a single machine. And if you do the math, then that corresponds to something like 320 gigabytes per second. And if you know a little bit about the underlying architectures, then that's actually way more than the theoretical bandwidth of the CPU, which would be around like 90 gigabytes per second, right? So the only way to actually achieve this is by doing other tricks like columnar processing, which Spark already does. So we're using all these kind of tricks and then some to get this kind of performance. Okay. So all in all, this so far has been a research project. So we're a university. We've been developing this for about 9 months now. But we actually think this is something that would be very interesting also to get some outside feedback on. So we've set up a little website here, and we've launched a private beta program, right? And we're very interested to get in touch with companies and get some more use cases to see how it works. So if you're a Spark user and you think performance is a problem for you, then please come talk to us and grab some flyers on the way out. So all of this was only possible because I have some really outstanding students, right? So Greg, Ruby, and James have done most of the work on this project, and Greg and Ruby are actually in the audience. So if you have any technical questions, then they will be happy to help you. And I think that's all I had, and I'm happy to take your questions.
All right, do we have any questions? Over there.
Hello, what is the limits for input and output?
What are the limits? Yes, good questions. I don't know. I'd be very happy to explore more and see, okay, well, what kind of things we can't do. So far, some of the things we don't yet support is actually distributed execution, right? And so we're only focusing on big machines with big memory. So we don't do any actual network communication. So that's something that if you really need to scale beyond, let's say, 1 terabyte of data, then that's not something we can do right now. Otherwise, I think it's a very general technique, right? So basically, it's a query compiler. So anything where you know what kind of code you want to generate, what kind of code patterns you want to execute, then there is a way to generate it.
Hi, thanks for the nice talk. What portion of the DataFrame API do you support today? Is it already extensive coverage, or is it only a small portion? Or?
So it's pretty extensive. I mean, we can handle the full TPCH suite. So there are joins, there are different kinds of joins. There are semi-joins, anti-joins, outer joins. There are things like various kinds of string comparisons with certain kinds of regular expressions and so on. So I think it's not 100% complete, but it's fairly general, right? So we can run pretty realistic things right now.
Anybody else?
What was the reason of not putting the code compilation down on the RDD level and getting kind of the distribution then for free? Because of course operations are also kind of executed on the executor level, on an RDD level as well.
Yes, very good question. So the reason, or sort of one way we really get performance, is by doing not just whole stage query compilation, but really whole query compilation at once, right? So we can generate a single piece of code and optimize that, right? And if you ship that to a C compiler or to LLVM, then the downstream compiler will do a good job on even in some cases auto-vectorization and so on, right? And those things you can only do if you really view the whole query as one piece of code, right? So if you start chopping things into chunks again, then that's much harder. And as I said, we don't need fault tolerance, and we don't need the bookkeeping that's associated with fault tolerance.
You said the resilience you basically omitted in favor of performance. Does it mean that you will always be more performant than any Spark engine, very optimized? If they go very fast on optimization, will they catch up, or will you always have an advantage by throwing resilience to the garbage?
So I think there will always be some advantage of not using any resiliency or fault tolerance mechanisms underneath, right? Because whatever you do, there's some kind of overhead. I think you could get the overhead pretty small, and sort of if you would integrate something like we did into the main Spark engine, then probably you would also get performance that is much closer than just now, right? But I think one of the key differences is really that Spark right now runs on the JVM, and there are certain limits to what you can do on the JVM, right? Without going to first off-heap memory and then actually native code generation. So I think native code generation is really one thing that gets you at least a speed up of several factors here.
Since you're on one machine, so did you compare to something like Pandas, which also comes with C bindings and is pretty fast?
So we have not compared to Pandas. We have compared to other database systems. For example, there's the Hyper database system by TU Munich, which is, I think, one of the fastest database engines out there. And sort of we're on par with them. Sometimes we're faster, sometimes they're faster.
Anybody else?
Yep, this one.
Since the JVM is doing just-in-time compilation, it's a bit flawed to compare when you just start the JVM. It's not even warmed up, so it's not like the cruise speed, and you stop it again. What I mean is the performance gap you get might be reduced if you just leave the JVM run longer and reach a cruising speed.
So that's a good point.
Have you measured that?
That is a good point. I mean, the query I showed you, I ran a couple of times before the talk, right? So, and it's actually a good question how the JVM actually does the warm up, right? And if you generate JVM bytecode on the fly, then the JVM has to warm up every time you execute this newly generated bytecode, right? Sort of there's a very fine line to walk, and that's one of the things that is very difficult with getting good performance out of the JVM, of actually seeing, well, how often do you have to run things, and also the JVM has different optimization paths, whether you're generating something that is a loop, and sort of in the middle of the loop execution you figure out, well, now this has become hot, now I need to compile, then it will do something that is called on-stack replacement. And that's a different compilation path than if you know, okay, this method has become hot and it is compiled at a certain point, right? And if you're running queries, then, well, chances are that you are executing this dense loop, right? So you might use the on-stack replacement compilation, which is not always as efficient as the regular just-in-time compilation. Right? So all of these things are really stuff where you need to have a lot of knowledge about the JVM, and you have to sort of very, very precisely tune what you are doing, right? And this is something that's, I mean, there are certainly consulting companies who are making a business out of this, but sort of for average users, it's a very hard problem.
With Flare, can you run out of memory when you want to load big data on one computer?
Yes, so can we run out of memory? Yeah, we can run out of memory, and we can also, before we actually run out of memory, things might get slow because the operating system will might decide to page something to disk, for example, right? So that's certainly something that can happen. So if you want to run on larger data than you actually have main memory, then, well, you have to be aware that there will be some shuffling to secondary storage. But as I said, you can buy a terabyte of memory, and sort of you can do a lot of things in a terabyte, right? So many practical applications are sort of in the tens or hundreds of gigabytes range.
Can I use user-defined functions?
That's another very good question. Yes, so within limits, right? So we have you can't use any kind of Scala code, right? But you can write the user-defined functions in a sort of stylized way, and then there's a certain API that we can support. Yeah, so this goes back to the graph I showed, where you basically have a set of domain-specific languages, right? So if you use any of the other domain-specific languages the compiler toolchain knows about, then you can merge them and put them together, right? And this is something that we are right now working actively on to see, well, can we extend this towards machine learning toolkits and so on.
So could you use this on Hive as well?
Good question. I don't know. We haven't looked at it. Yes. So what does it mean to use it on Hive? That's the question, right? I think it would be an interesting thing to look at. Yes. Yeah. So I think, yeah. So I mean, in any sense, we can sort of use Hive and then bypass it and do our own thing on the side. So that's something we can certainly do. Yes. So the question was talking about user-defined functions. Can we plug in our own C++ library? And yes, that's something we can absolutely do. Yes.
One question about how to debug this stuff. I mean, this is generating C++ code I'm not aware of as a Scala developer of this. Have I some possibility to break points, or how can I look inside what's happening if I'm forced to because something is not working?
Yeah, good question. So I think it depends what kind of user you are, right? If you're an end user and you're just using this to accelerate your queries, then so hopefully the chances are that you will not actually have to look at it, right? If the system works and everything is kind of correct, then that should not be necessary. But that said, you can certainly go and inspect the code. So for example, we can take a look at some of the things we generated. And so I mean, it's not super pretty, but sort of you can look at it, and we can even generate some comments to say what's going on. So here we know that, well, there's the table scan, right? That's where it starts, and we can also insert some more hints. Okay, which query operator does a certain statement come from, and kind of tie that back to the source, right? And we can. So one of the nice things I think is that we can actually dump this to a sort of closed C file, right? And then you can even launch this file on your own and use GDB to debug it and do any kind of profiling or other debugging that you want on this level of native code.
All right, we're running up against the limits of our time here, and I want to make sure that people have time to get on to their next thing. So why don't we give our speaker another round of applause? And if you have further questions, why don't you just pull them aside offline? You can ask those.
And if you're interested, please grab a flyer on the way out. Thanks.